Hello guys. Welcome to our chemical kinetics session. Okay. Yeah. So this is going to be an exciting session. There's quite a number of things to be learned, and yeah, it's going to be very brief and sweet. Daisy, hello. Phineas Lungu, hi. I hope you guys can hear me clearly. Can you get me? Lucky, hello. Can you get me? Are you able to get me clearly? All right. So chemical kinetics. It's quite an interesting session because we've been using the notes to look at chemical equilibrium. So chemical equilibrium is going to look at, rather has been looking at a special balance when the forward reaction is equal to the reverse reaction and so on. Yeah. Then chemical kinetics now is going to look at the speed of those reactions. So speed of those reactions. Okay. So speed is basically the same as rate. Okay. All right. Hello, Maxmina, Luena, hi. Yeah, this is great. Okay, people are geared to learn today. In a few seconds, we already have 77 viewers. Interesting stuff. Okay, so I think we can start. We can start. Okay. So, chemical kinetics. Chemical kinetics, basically, we will be looking at the speed or the rate at which a chemical reaction, Nasilele, hello, chemical reaction occurs. Caster, hi. Yeah, okay. So chemical kinetics, we're basically looking at the speed or rate at which a chemical reaction occurs. Under chemical kinetics, what are we going to have under chemical kinetics? So I wrote up a skeleton for you guys, and this would be in the document as well. This would be in the document. So here's a skeleton of chemical kinetics. First of all, you need to understand. I think we can start. Get your books, prepare your rulers for the perfectionists, prepare your calculators, and let's get started. Okay, so chemical kinetics. What is the skeleton of this topic? Because if you understand what we are going to talk about, or you have an idea where we are going, it's easy for you to follow. Okay, so firstly, you need to understand what rate is with respect to reactions. Okay, so rate basically refers to how fast are reactants being used up, or how fast are products forming. You get? Yeah, like you're eating fish with your friends. So we'll be looking at how quickly the fish is disappearing, okay, and how quickly the bones of the fish are appearing. You get? So there's the fish, that is the reactant, which you are consuming, and then there's the bonds that you are producing. You get? So anytime you consume something, there's always something produced. Okay. Then we're going to introduce an ordinary way of calculating the rate of a reaction according to the balanced chemical equation. Okay. So subtract for reactants and add for products. I'm sure you remember something like this on the ICE table. Okay, next, we'll talk about a special relationship that connects the rate to a constant K, the concentration and the powers. So powers will now be referred to as orders. All right. And then at the end of it all, you're going to have to know three more things. How do you find the powers? And the rate laws. We're supposed to know integrated rate laws and then the Arrhenius equation. So we'll do what we can today. How do we divide our time effectively for the session? Okay, I think we'll have a session just to help you make a plan for your sessionals. So don't worry about that. So that's what we are going to do today. We'll try and cover as much, but then obviously this is one session and we can't manage to cover everything. I think we can start. Okay, so chemical kinetics. Chemical kinetics. We are referring to the speed or rate at which a chemical reaction occurs. Okay. Now, I'm going to go straight to chemical kinetics and equations. Imagine you've been given a chemical reaction, okay? A plus B reacting to give us C plus D. Okay, now you know each and every chemical reaction is going to have balancing numbers. If there's no balancing number, then the balancing number is 0. So we're just going to put general letters there to signify balancing numbers. So P, Q, R, S. So these are our balancing numbers. Then a question might state to say, write expressions for the rate of usage or formation of each reactant and each product. Okay, so you've been given a general chemical equation and then they want you to write an expression for the rate of usage and rate of formation. Now there are some key things here, keys. Reactants disappear, while products appear. Now, if something is disappearing, then it is reducing in quantity. If something is appearing, then it is increasing in quantity. Now, you need to understand what the word rate means. Rate is basically change in amount divided by time. Okay. Now, because we are looking at reactants and products, the change in amount, obviously, we're going to refer to moles. Okay? And these moles are going to be in a specific volume. So, basically, rate is going to be change in concentration. Remember, I'm just from telling you that these moles are going to be in an enclosed space. So moles divided by volume is going to give us concentration. So change in concentration divided by change in time. Okay. Basically, rate is going to be change in concentration. Now, you guys should have learned from chemical equilibrium that we use square brackets to show that we are dealing with concentration. Okay, so change in concentration, this is going to be rate, is equal to change, we are going to use delta, so change in concentration of something, divided by change in time. Okay. Now, there's a part, I'd like you guys to write this. There's a part of chemical kinetics that is interested in coefficients, and there's a part of chemical kinetics that is not interested in coefficients. You get? This part of chemical kinetics is interested in coefficients. Only this part. Only this part. And I want you to look at the question properly. They're not asking you to write the rate law. If they ask you to write the rate law, we are not interested in coefficients. But a general rate expression is interested in coefficients. I'll emphasize that when we reach that point. So this part is interested in coefficients, right? But the part that we're going to do after this is not interested in coefficients. So chemical kinetics has two parts. There's the first part that is interested in coefficients. There's the second part that is not interested in coefficients. Okay. Coefficients and rates. And rates. Okay, there's a lot that I need to introduce you to. And I know most of you have tried studying this topic, so some of these things are not entirely new. So coefficients and rates. We said we have A reacting with B to give us C and D. And then the coefficient of A is going to be P, so Q, R, S. Now, these are reactants. These are products. What do you think will happen to reactants? You can comment. What do you think will happen to reactants? Are they going to be reducing or they're going to be increasing? What do you think will happen to reactants as the reaction proceeds? Will the reactants be reducing or increasing? You can comment what you feel will happen. Quickly, I'll give you 3-4 seconds. What do you think will happen to the reactants? You can comment. Just to make sure we are all on the same page. Okay, so reactants will be reducing. Let's see. If 2 more says the same thing, then we know people are following. So reactants will be reducing. Excellent. So reactants will reduce, but products will increase. Right. And if my money reduces, for instance, initially I have 100 kwacha. And finally, I have, if my money is reducing, my fine will always be less. Maybe finally I have 50 kwacha. The change in the money that I have is going to be final minus initial. So you will notice that this is going to be 50 minus 100. Whatever answer I get, 50 minus 100 is going to give me negative 50. So anytime something is reducing, the change is negative. Okay, pay attention to that part. Anytime something is reducing, the change is negative. Now, we can, just from this thought process here, you can tell that if something is reducing and it's then its change will be negative. Then if something is increasing, then its change will be positive. And it is for that reason that the rate, okay, let's call this general rate, the general, because we're going to say we have the general rate and we have the rate law. Zona ishila na voice yenu. Wait, you can hardly hear me, but your friends are able to get me. So try watching this video again tomorrow if things are not too clear. Okay. All right. So we're going to call the first rate the general rate. So the general rate is interested in coefficients. Okay, next, the general rate has a negative associated with reactants. And if reactants are associated with a negative, then products are obviously associated with a positive. And a positive with products. Okay. And now, we also mentioned that coefficients have a role in the expression. So, remember we had we had A reacting with B to give us C and D. And then these are the coefficients. How do they relate? So let me show you how to write the rate for reactants. Okay. So, rate. Pay attention to this. Rate. Because this is a reactant, we are going to have a negative. Why do we have a negative? Because its concentration is reducing. If the concentration is reducing, then delta, which is final minus initial, will give us a negative. So rate is going to be negative. Okay? Negative shows us that we're dealing with reactants. So negative 1 over, pay attention to this. Pay attention to this. The balancing numbers are important for the general rate. Okay. The balancing numbers are important for the general rate. How are they important? It will be 1 over the balancing number. The balancing number for A is P. So it will be 1 over P. You get? Then we're going to put delta. Delta means change. Then if I put A in square brackets, what do you think I am referring to? What do you think A in square brackets means? What do you think A in square brackets means? So that we make sure everyone is following. What does A in square brackets means? What does it mean? What does it mean? If you put something in square brackets, what are we referring to? We are referring to the concentration of A, yes. So there's this delta. This delta means change in the concentration of A. And I showed you that for reactants, the final will be less than the initial. So when you subtract F minus I, we're going to end up with a negative. So it will be 1 over the balancing number times change in concentration, okay, of A divided by change in time. You get? Next, the rate for B. The rate for B is going to be negative because it is a reactant. 1 over balancing number is Q. Okay? Then delta, concentration of B divided by delta T. You understand why these are negative? Because these are referring to reactants. And reactants are reducing. And the negative and the balancing numbers only appear when we are writing an expression for the general rate. Okay. Very soon we'll start dealing with the rate law. Now, the expression for the products will be slightly different. Remember we said products increase, reactants reduce. So this is going to be rate is equal to this will be positive because the products will be increasing. Why are you putting 1 over P instead of P alone multiplied by the concentration? So the relationship has been found to be an inverse relationship experimentally. So that's the standard that we are adopting. Okay. So for products, it will be positive 1 over R multiplied by delta concentration, change in concentration of C divided by change in time. Okay, for the last one, it will be rate is equal to positive 1 over S delta D divided by delta T. Now, I want you to notice something. All these are for the products. Okay? Products, they have a positive. Reactants have a negative. All these things are referring to the same thing, which is the rate. So we can use the transitive rule, and I can basically say rate is equal to negative 1 over P delta A divided by delta T is equal to negative 1 over Q delta B divided by delta T is equal to positive, you get? Positive 1 over R delta C divided by delta T. And then you can continue, you can include D as well. So that's how you write an expression for the general rate. Now, this is very minor stuff when it comes to chemical kinetics. Let's quickly go to the rate law. Okay. We don't have a lot of time, so we have to try and cover as much as we can. The document is coming. The document is coming. Okay, so we can write a title and we'll call it the rate law. So I want you guys to understand that there's a big difference between the general rate. The general rate relies, the general rate includes negatives and it includes positives depending on whether you're looking at reactants and products. Okay? The general rate looks at whether you're looking at reactants or products. And then the general rate is also interested in balancing numbers. You get? We're now looking at the rate law. The rate law is very different from the general rate. How is it different? Number one, rate law is always a positive expression. Okay, the generate could be negative if you are referring to reactants, but rate law is always positive, always, and then we're not referring to COVID-19. Okay, next, number two. Rate law ignores balancing numbers. Balancing numbers. The same way that some of you are ignored by your crushes when you text them is the same way the rate law is going to ignore balancing numbers. So rate law ignores balancing numbers. It doesn't care about them. Okay. Then, what else? So the rate law introduces a constant K, which we are going to call the what? Anyway, it's basically just which we are going to call the rate constant. Okay, and this rate constant, units are important. Units are important. But if you remember, chemical equilibrium, the constant there, units were not really important. Okay, then number 4, the rate law. The rate law has an order. Okay, so order basically just refers to powers. Okay, and then the behavior of that particular reaction depends on the overall powers. So for rate law, the key thing is how does one find powers. Okay. So rate law, the general form of the rate law is going to be rate is directly proportional to the concentration. Oh, let me include this. So rate law only cares about reactants. Chapwa. The rate law is only interested in reactants. But the general rate could also include products. Rate law is always positive. Despite it being interested in reactant, it will still be a positive. But for the, rate law is always positive. But for the general rate, if you're dealing with reactants, it's going to be negative. So rate law is going to be concentration of A, which was a reactant, to the power X, multiplied by concentration of B to the power Y. Now, I want you to notice that the original reaction was A plus B, and the balancing number for A was Q, balancing number for B, or rather was P, balancing number for B was Q. Notice that P and Q have no place in this expression. You get? Once again, the rate law is not really interested in balancing numbers. Okay. So let's go. So we've said the general form of the rate law is going to be rate is directly proportional to A to the power X and B to the power Y. I told you that the rate law is interested in what we call the order. The order is the same as the overall power, or the power in short. So these two are powers. Okay? Then proportionality constant. What do you guys did math? What do you replace the proportionality constant with? Any ideas? What do you replace this proportionality symbol with? What do you replace this alpha symbol with? When you're dealing with proportionality, what do you replace this with? Anyone with an idea, what do you replace this with? I think you remember this. P varies directly as Q. What? You did these things. What do you replace this symbol with? Who can remember? K. Are you sure it's just K? The constant K. Nope. It's not K. Continue, keep trying. An equal sign and a K. Excellent. So you replace this proportionality sign with an equal sign and a K. So this becomes rate is equal to K, A to the power X, and then B to the power Y. You get? This K is what we call the rate constant. This is the concentration, or these are concentrations. This is the concentration of A, concentration of B. Overall, these are the powers. So I'm going to say X plus Y is equal to overall order. You're going to see how these are going to work. Now, the hardest part of this topic is finding this same X and finding this same Y. How do you go about finding X and Y? So I'm going to do an exam question and we'll see. We'll see how everything plays out. So let's go. Where's the exam question? I wrote it somewhere. Okay. Here we are. This is what a typical question will look like. This is what a typical question will look like. Okay, so let's read it together. Nitrogen reacts with hydrogen to form ammonia gas. Okay. And we are fortunate enough to be given an expression, actually an equation. So N2 plus 3H2 blah 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 blah. 3 experiments are conducted and the data below is collected. So we are doing all this in order to find what X and Y is. So this is experiment 1, that's the data that has been given, and so on. So part A, what is the rate law for the reaction above? So instead of having A and B and C and whatever, they instead, so instead of having A and B, they instead want you to put the actual reactants there. So our reactants here in this expression are going to be nitrogen and hydrogen. Okay, so instead of having A and B, we are basically just going to put nitrogen and hydrogen gas. Remember, for the rate law, we are not really interested in the balancing numbers. So rate law is completely going to ignore these balancing numbers. Okay, so part A, what is the rate law for the reaction above? Part B, what is the overall order for the reaction? So overall order, remember I told you that overall order involves finding X and Y and then adding them. The overall order is basically X plus Y. What are X and Y? What are they representing? X and Y represent X is the power of A, Y is the power of B. How do you find X and Y? That's the key thing under this topic. Okay, so part 1, what is the rate law? Part 2, what is the overall order of the reaction? And then part C, what is the value of K, the rate constant with its units. So they want you to find the value of K. They're also interested in the units. Okay, so you can put a point. You can put a point. We find the powers by dividing experiments. Okay. Nakwenda na limbo, you're able to listen. Me, I can't even see anything. Okay. Oof. Is network that bad now? Can you guys hear me? Can you get me? Just comment if you're able to hear me so that no one is left out. Are you guys able to hear me? Just quickly comment if you are able to get me. Andrew is able to hear me. Brown is able to hear me. King is able to hear me. Joseph is able to hear me. So I guess network my end is okay. So you guys will maybe have to try and watch the video tomorrow. So if you can't follow through tonight, try and watch the video tomorrow. Okay. So how do we find the powers? We find the powers by dividing experiments. Now let's start answering this question in full. Part 1, they've given us this chemical equation, okay, and they've given us this data. They want us, first of all, to write the rate law for the reaction above. Rate law. So rate law is basically an expression that has the rate, the K, the concentration, and powers. Chapwa. For the powers, you can just put X, Y, and if you have a third one, you can put Z. So rate law. Here we have N2 reacting with H2, giving us NH3. To balance this, we're going to put a 2 and we're going to put a 3. Here is a question. Does the rate law include balancing numbers? Does the rate law include balancing numbers? No or yes? Does the rate law include balancing numbers? So the link will come when the session is done, and then we'll post it in the group. So does the rate law include balancing numbers? No. The only thing that includes balancing numbers is the general rate. General rate is different from the rate law, and I gave you those differences, right? So make sure you find time to watch this video again so to just cement everything. Rate law. Basically, and then one other question. What is the rate law interested in? Is it interested in products or reactants? Like, what is it interested in here? Are we interested in the reactants or are we interested in the products? What is the rate law interested in? Reactants or products? What is the rate law interested in? Is it the reactants or is it the products? What is the rate law interested in? Is it reactants or is it the products? So the rate law is interested in reactants. Excellent. So we have two reactants. So let me just put some pointers. So focus on reactants only. Okay. Next pointer, ignore balancing numbers. Next pointer, don't include a negative. Okay, so these are the three things that you should keep in mind. So rate law, basically for this is going to be rate is equal to K, open brackets. The first set of brackets is going to be for the first reactant, and the order doesn't matter. Okay, so this is going to be N2, and then this is going to be H2. Ignore balancing numbers. We don't know the powers yet, so I'll just put X and I'll just put Y. It doesn't matter. If you want, you can put A and B. It doesn't matter. Data and data. Okay, so just this expression is your answer for the rate law. Chap, you're done. That's with part A. So part A was asking, what is the rate law for the reaction above? So rate law basically is this expression before you find the X and Y. Chap. Okay. Benson, try switching off your data, putting it on flight mode, and then you bring the network back. Maybe you'll be able to see then. Okay, so that's part A. This is how we write the rate law. Now, part B. What is the overall order of the reaction? I need you guys to pay attention to part B, because this is where things start getting hectic. I really need you to pay attention to part B. Overall order. In order for me to find the overall order, I need to find the X and I need to find Y, and then I need to add them. So before I can even find the overall order, I first of all need to find the X and Y. Okay, X and Y refer to the powers. Okay, X and Y are the powers. We get the powers by dividing experiments. Remember the first thing I wrote? We find the powers by dividing experiments. Now, what experiments do we divide? If you look at this data that has been given, we've been told that in experiment 1, we have experiment 1, experiment 2, and experiment 3. Sometimes you can even have up to 4 or 5 experiments. So, you divide experiments. So it will be maybe, now how do you know what should be, when you divide, something should be a numerator, something should be a denominator. You want an item that is larger to be your numerator. You want an item that is larger to be your numerator. For instance, if I have experiments 1 and 2, okay? If I have experiments 1 and 2, which one do you think should be our numerator? If the numerator is supposed to be bigger. Between experiments 1 and 2, when we say bigger, we are looking at the rates. Between experiments 1 and 2, which one is supposed to be bigger? Between experiments 1 and 2, which of the two is supposed to be the numerator rather? So experiment 2 is going to be the numerator, and then experiment 1 is going to be the denominator. So you want the experiment with the larger rate to be the numerator, and you want the experiment with the smaller rate to be the denominator. Okay, so let's write those pointers. So B, finding the powers, powers. So the first pointer is going to be, you want the experiment with the larger rate to be the denominator. Oh no, not denominator, to be the numerator. Okay, that's the first pointer. Pay attention. The second pointer is, so I said if my focus is 1 and 2, 1 is going to be my numerator and 2 is going to be my denominator. Next, you don't just choose chintobe ntobe. Let's do this. Don't choose chintobe ntobe. Be strategic. Strategic. Now, what do I mean when I say strategic? The second thing that you should keep in mind is you always want to divide. Like the first time you divide, you always want to divide experiments that have the same concentration. You always want to divide experiments that have the same concentration. At least one concentration should be the same. For the first division, at least one experiment for the first division, at least both experiments should have one concentration being the same. Okay, so if you look at this, if you look at experiment 2 and experiment 3, they have the same concentration, even though these are different here for hydrogen, but for nitrogen they are the same. You get? If you look at experiment 1 and experiment 3, the concentrations of hydrogen are the same. So the first time you divide, at least one concentration should be the same. Okay, so let's just quickly run through. Number 1. So rather, how do you find the powers? Number 1, you want the experiment with the larger rate to be the numerator. Okay? So don't choose chintobe ntobe, be strategic. What do we mean by be strategic? For the first division, at least both experiments should have one concentration being the same. So we have a choice here. I can either go with experiment 1 and experiment 2, or experiment 2 and experiment 3, or experiment 1 and experiment 3, or you get the order. It's up to you to choose. Now, if you look at these experiments, like we want 2 experiments that are going to, number 1, at least 2 of the concentrations should be the same. So I can either go with 2 and 3 because these will be the same, or I can go with 1 and 3. You get? Which one do you want us to use? 2 and 3 or 1 and 3? Both are correct. It's up to you to choose. As long as that criteria has been met to say one of the concentrations should be the same, then you're free to choose those 2 experiments. Which ones do you want? Do you want us to go with 2 and 3, or you want us to go with 1 and 3? Okay. Two and 3. Okay. I'm giving you the illusion of a choice. So we are going with equations 2 and 3. Okay. 2 and 3. Anyway, 2 and 3 wins already. Mwebadera ndabambi idekenifye. Akupozenifye amanoko. So, experiments 2 and 3. So, divide EXPTs 2 and 3. Now, 4 and 5. Now, 4 and 5. All right. So, divide experiments 2 and 3. Now, we need to be careful here. We want the experiment with the larger rate. Remember, this row is representing rates. We want the experiments with the larger rate to be the numerator. We are starting with experiment 2 and experiment 3. Okay? Experiment 2 has a larger rate than experiment 3. You get? So basically, this is going to be 2 divided by 3. Fine. I hope you guys are following. So, after choosing what experiments to use, substitute both into the rate law and divide the expressions. So we're going to divide 2 and 3. 2 is going to be the numerator because it has the larger rate. Larger rate. 3 is going to be the denominator because it has the smaller rate. Why did we choose 2 and 3? Because at least they have one concentration being the same. Fine. Okay. Next. So after choosing what experiments to use, substitute both into the rate law and divide them. Remember, the rate law was rate is equal to K concentration of N2 to the power X multiplied by concentration of H2 to the power Y. So I'm going to substitute twice into this. And then I'll divide those substitutions. So for EXPT, I'll start with experiment 2. So for experiment 2, we substitute for experiment 2. We substitute for experiment 2. So what do we substitute for experiment 2? We are going to substitute in the rate law. So for experiment 2, where I have rate, guys, pay attention. For experiment 2, let me just go through everything that I've done. Number 1, you choose what experiments to divide, and I've told you the criteria to use. Number 2, after choosing what experiments to use, substitute both into the rate law and divide them. You get? So we have chosen 2 and 3. Now we're going to substitute experiment 2 into the rate law, and then we also substitute experiment 3 into the rate law. You get? So how do we substitute experiment 2 into the rate law? So EXPT2 into the rate law is going to be where I have rate, I'm going to put, so where I have rate, I'm going to put the rate of experiment 2. Remember, this row talks about the rates. This is the concentration of hydrogen, concentration of nitrogen. This row here talks about rate. The rate of experiment 2 is 4.8 times 10 to the power negative 3 m per s. Now, we'll deal with units later. For now, let's just deal with values, okay? So, where I have rate, I'm going to put 4.8 times 10 to the power negative 3 is equal to, I don't know what k is, so I'll leave it blank, okay? So, it should just be k, open brackets. We are dealing with experiment 2. What was the concentration of nitrogen in experiment 2? Nitrogen is here. Concentration of nitrogen is going to be 0.10, and then we don't know the power because we're looking for the powers. That would be everything to the power x. Okay. Next, rate law was nitrogen to the power x and then hydrogen to the power y. The concentration of hydrogen in experiment 2 is 0.04. Okay. So this is going to be 0.04. Let's just include this 0 and then everything to the power y. This is my substitution in experiment 2. Do you see? I've substituted the rate law. I've substituted the rate with the rate for experiment 2. K, I don't know what K is. I've substituted the concentration of nitrogen from experiment 2 and the concentration of hydrogen from experiment 2. Now, we said experiment 2 divided by 3. This is experiment 2. Okay? Let's now substitute in experiment 3. EXPT 3. Substituting in experiment 3. Okay, so this is the data for experiment 3. This is for nitrogen. This is for hydrogen. Pay attention, guys. Pay attention. The rate law here, this is concentration of nitrogen. Concentration of hydrogen, this is the rate. The rate for experiment 3 is going to be 1.2. So this is going to be 1.2 times 10 to the power negative 3 is equal to K, open brackets, concentration of nitrogen in experiment 3, where's nitrogen here? In experiment 3 is going to be 0.1. 0.10. Everything to the power x. Okay? Concentration of hydrogen in experiment 3 is going to be 0.010. Everything to the power y. We said we are going to divide experiment 2 by experiment 3. And I want you to pay attention to the way that I've written them. I've written what I want us to have as our numerator on top. And then I've written what I want us to have as our denominator below. So I'll just put an over to divide the two expressions. This is basically experiment 2 divided by experiment 3. Okay. Let's go. Pay attention to this part. It doesn't really matter what brackets you use when substituting. It doesn't really matter. It doesn't really matter. Okay. Now, I want to show you why it was important for us to have at least one experiment having the same concentrations. We're dividing this by that. We're dividing K by K. We're dividing this by that, that by that. We want as many things as possible to disappear. We have K on top and we have K below. What do you think will happen to the Ks? What do you think will happen to the Ks? Mind you, at the end of all this, all you want to find is X and Y. What do you think? What do you think will happen to the Ks when we divide? What do you think? I have a K on top and I have a K below. What do you think will happen? Yes, they will cancel out. So K on top cancels out with K below. Whenever you have the same thing on top and below, it just disappears. Now, pay attention to this concentration. That's why we wanted at least one concentration to be the same. Okay? The concentration here on top, this is 0.10 to the power x. Below, I also have 0.10 to the power x. This is the same thing. So the same way that the k's have cancelled out is the same way that this concentration will cancel out. So, pa. Okay? Even the power x disappears. This power x disappears. Do you see that? The same way that k has cancelled out is the same way that the concentrations will cancel out. You get? I hope you guys are following. I hope you guys are following. Okay, next. So it will be this divided by that. Okay, I hope you guys are able to see. Now, some of your calculators are not able to do this, so just make sure you know your calculator well. This is going to be 4.8 times 10 to the power negative 3. I hope you guys are able to see. 4.8 times 10 to the power negative 3 divided by 1.2 times 10 to the power negative 3 as well. So this divided by that. Okay, you see I've put it in my calculator. Divide this, we get a 4. That's why you want your numerator to be larger so that you get a whole number. If your numerator was smaller, you're going to get a fraction. Okay, so this divided by this will give us a 4. Okay, we had an equal sign here. Equal sign obviously won't cancel out. So I had an equal sign here, so I'll put an equal sign. So 4 is equal to, the k has disappeared, no need to write it. The first concentration has disappeared, no need to write it. Now here, I am going to divide this into that. And my answer will still have a power of y. You get? So this is going to be 0.040 divided by 0.010. Okay, so I can divide what's inside and then my answer will still be the same power. Will there be an instance when you don't get a whole number? You always get a whole number if you do the right thing. Okay, if you don't get a whole number, chances are you made the larger one be a denominator. Okay, so this divided by that, that's going to give us 4. And remember, we had the power of y, so this is going to be everything to the power y. Is it okay to assume that when you divide and get a whole number, then you're doing the right thing? Yes, excellent. Excellent. Now, this is 4 is equal to 4 to the power y. This 4 doesn't have a power. So this 4 is as good as being raised to the power what? If 4 doesn't have a power, then it is as good as 4 to the power what? If 4 does not have a power, then it is as good as 4 to the power what? Okay, it's as good as 4 to the power 1. Yep. So basically, this is 4 to the power 1 is equal to 4 to the power y. And you guys know that if the bases are the same, you can simply equate the powers. So you end up saying y is equal to 1. At least we now know what y is. Y is 1. Our next step is to find x. Is everyone okay up to that level? In case you don't understand some part, you can always rewatch this video. Just skip forward up to this part. Won't the y cancel out as well? No. The y will not cancel out because these are not the same things. These cancelled out because they were exactly the same things. And if the y cancels out, then what are we solving for? You get? So if everything cancels out, everybody you understand? This topic is beautiful. All right, let's go. you now know how to find y. And we found y by substituting 2, by using equation 2, rather experiment 2 and experiment 3. Now, we need another pair in order for us to find x. And that other pair, the criteria, preferably the criteria should be the same, but then the second substitution doesn't really matter. Okay, so for the second substitution, I'm trying to look for the power of, I've managed to find y, which is the power of hydrogen, right? I'm now going to find x, which is the power of nitrogen. Okay. Keep in mind that we found y to be 1. Okay. I need 2 experiments to divide. I've already used 2 and 3. Now, it's possible for you to actually use one of these experiments more than once. You get? So for the next one, it doesn't matter what I choose to use. I can use 1 and 2, or I can use 1 and 3. You get? I think 1 and 3 is better because these are going to cancel out. You get? But at the end of the day, it doesn't matter what I choose to use because I know I have y. Okay, so I'm going to substitute 1 and 3 and then divide them. Now, let me decide in advance which of these 2 is going to be the numerator. So I've said I'm going to use 1 and 3. 1 has a larger rate, yes. 3 has a smaller rate. So 1 is going to be our numerator. So this is going to be EXPT1 divided by EXPT2. Okay? And remember the rate law. Where is the rate law? The rate law was concentration of nitrogen to the power x, concentration of hydrogen to the power y. Nitrogen to the power x, hydrogen to the power y. Nitrogen to the power x, hydrogen to the power y. So it's experiment 1 divided by experiment 2. Okay, let's go. So experiment 1. The rate for experiment 1 is 2.4. 2.4 times 10 to the power negative 3. Okay, is equal to concentration of nitrogen to the power x. Concentration of nitrogen for experiment 1 is 0.20, and this was being raised to the power x. Okay. Next, this is going to be concentration of hydrogen, which is 0.010, everything to the power y. Okay? Yeah, we are done. Divided by experiment 2. The rate for experiment... Oh, sorry. Did you say 1 and 2? Oh, 1 and 3, yes. 1 divided by 3, thank you. So, for experiment 3, this is going to be, the rate for experiment 3 is going to be 1.2 times 10 to the power negative 3 is equal to, open brackets, concentration of nitrogen is going to be 0.10, everything to the power x. Concentration of hydrogen for experiment 3 is going to be 0.010, everything raised to the power y. Now, you can go about this question in 2 ways. You know that y is 1, and you can substitute 1, 1. But at the end of the day, we're going to have the same item here and here. So they will cancel out. Excellent. So this cancels out with that. So you can only cancel out the powers if the bases are the same. You get? You can only cancel out the powers if the bases are the same. Next. Oh, we've left out k. Okay. Anyway, but we know it cancels out. Okay. So k will cancel out here, k will cancel out here. So this part has cancelled out, the k has cancelled out. I'm left with this part here, and I'm left with this part here. Now, you know how these powers are the same, they'll cancel out. 2.4 divided by 1.2 obviously will give us 2. So this into that is going to give us 2. There is equal to. Now, here, if the powers are the same, we can divide the bases. So this base into this base. And you can tell, and let me just use the calculator. We have doubting Thomases here. So 0.20 divided by 0.10. We get a 2. So this is going to be 2 to the power x. The bases are the same, and this 2 doesn't have a power, so it's as good as being raised to the power 1, meaning x is equal to 1. So we have found x to be equal to 1, and we have found y to be equal to 1. The question was asking us to say, the first part of the question was, what is the rate law for the reaction above? Rate law was this expression. Where is it? Rate law was basically this expression, okay? Then part B, what is the overall order of the reaction? What if the bases come out different? You're given data that always works out. You're given data that always works out, so don't worry about such a possibility. So what is the overall order of the reaction? Overall order, I need to find the power x and the power y. Overall order is x plus y. Okay. I know what x is. X is 1, and I know y is 1. Is there a situation where the bases are not the same? Yes. Yes. For instance, I can get 1 is equal to 4 to the power x. Okay? In such a case, you know x is going to be 0. You understand? So x is 1, y is 1. So overall order is going to be 1 plus 1, which is 2. Okay. Yeah. Then they'll ask you next, quickly, so that we can conclude the session. I don't want this to be ridiculously long. The last part of the question, what is the value of k? And then they also want us to include the units. But let's find the value first. To find the value of k, what do we call k? What do we call k? Just type. What do we call k? We can use logs, maybe if bases are different. What do we call k in the rate law? I mentioned this when we just started. What do we call k? What do we call it? What is its name? What do we call k? The k in the rate law expression, what do we call it? It's not just a constant, it's called the rate constant. Excellent. Okay. So how do we find the value of k? Here's a tip. Okay, use the experiment that was used twice. Use the experiment that was used twice. Okay, let's go back to this. Remember, initially, we used experiment 2 and 3. Then, the second time, we used experiments 1 and 3. Which experiment was used twice? Which experiment was used twice? Between experiment 1, rather from these options, experiment 1, 2, and 3. Which of these experiments was used twice? Experiment 3 was used twice. Excellent. Okay, so we're going to use experiment 3. Remember, the rate law was rate is equal to k. So rate law was rate is equal to k, open brackets, concentration of nitrogen to the power x, concentration of hydrogen to the power y. Yep. Now, we know our x is 1. We know our x is 1 and we know our y is 1. And we're going to use the experiment that was used twice, which was experiment 3. So I'm going to substitute everything for experiment 3. I now have the rate, I have X, I have Y, I have the concentration, I have the concentration. The only thing I don't have is K. And you can get the value of K like that. So experiment 3, the rate is going to be 1.2 times 10 to the power negative 3 is equal to K. You get? Here, this is going to be N2, concentration of N2 0.10, everything to the power 1. H2, this is going to be 0.010, everything to the power 1 as well. Okay? Yeah, so make K the subject. Now, raising something to a power of 1 doesn't change it. So basically, this is just going to give us K is equal to 1.2 times 10 to the power negative 3 divided by 0.1 times 0.01. So K is going to give us that. Okay, so this is going to be, this is going to be 1.2 times 10 to the power negative 3 divided by 0.1 times 0.01. Okay, we're going to get 6 over 5, which is 1.2. So rate constant here is going to be 1.2. Now, what units are we going to have? Units. When making K the subject of the formula, recall that what we have on top is rate. So rate is going to have units of meter per second. Okay? This concentration had a unit of, or not meter per second rather, molar per second. This is going to have units of molar because it was being raised to the power 1. If it was being raised to the power 2, it would have been m squared. This was also being raised to the power 1, so it would just be molar. So the units are going to be molar per second, okay, divided by molar squared. So molar per second divided by molar squared, we simplify it. Let's just go to the next page. So we are dealing with the units, units. We have molar per second divided by molar squared. This is the same as the sign because what we have on top divided by what we have below. Okay. Now, this is as good as over 1. And then you don't divide fractions, you instead multiply by the reciprocal. This is going to be molar per second times 1 over m squared. Now, instead of writing m squared, I'm going to write m times m so that you can see any cancellations. So the m cancels out, the m cancels out. So my overall unit is going to be 1 over molar second. So K is going to be 1.2, okay, per molar second. You're done. You are done. That's a full question on chemical kinetics. All right, so that's that. So quick revision. Know what rate is. Rate is change in amount divided by time. Okay, then there are 2 rates. Summary. There are 2 rates. We can have the general rate, and we can have the rate law. General rate, are you supposed to do that every time, or the units for K are constant? So you're supposed to do it every time because next time you may have the concentration of hydrogen having a power of 2 maybe. You get? So general rate is interested in coefficients. General rate is interested in negatives. And general rate is interested in both products and reactants. Rate law is not interested in coefficients. It's not interested in negatives. It's just interested in powers. You get? And then rate law has a constant K. So basically, that's that. So the next things we're going to try and tackle in the subsequent lessons are, we are going to talk about the Arrhenius equation. Right. So Arrhenius equation is going to be K is equal to AE to the power negative EA over RT. All right, okay. K is the same rate constant that we are talking about. You get? E is the base that we use for logarithms. EA is what we call activation energy. Activation energy. R is going to be 8.314 joules per Kelvin more. Joules, that. Yeah, anyway, I can't remember the units here. And then T is going to be in kelvins as well. Kelvin. So just pay attention to these values that we'll be using, okay? And everything else. So Arrhenius equation, we're going to use it as a single entity. And then Arrhenius equation, we're going to use it when comparing two things. And we'll end up with an expression, okay? So that was what we had for tonight. It's been a busy day, but at least the lesson went on undisturbed. Have a very good night and all the best. See you in our next lesson. We will communicate when we meet next.